Okay, so we had some technical difficulties. We were still just going over some examples, a couple examples without using U substitution. Sometimes when we're rewriting these problems, we want to rewrite it so that we have our variable raised to a power. We can break this down where we can take the antiderivative, the integral of a term plus the integral of the next term, etc. We can pull our coefficients out front, just like if we were taking the derivative of like 5x squared. We could pull that 5 out and just take the derivative of x squared and multiply it by 5. So same sort of reason, we can pull out the coefficients in front of our integral sign and then take the antiderivative of the piece. So remember, taking the antiderivative, you're just adding 1 to your exponent and then dividing by that new exponent. And so adding 1 to our x squared, that is 3. So we have to divide by that 3. And then we add some constant c sub 1. So now I'm taking the antiderivative of 18/5 x to the 1/5 dx. So I have to add 1 to my exponent. So 1/5 plus, I'm gonna write that 1 as 5/5. So that gives me 6/5. And I have to divide by that new value, 6/5, plus some constant c. So we can simplify and clean this up. 3 goes into 6 twice. And so we have 2x cubed plus some constant, we called it c sub 1. Divide by a fraction, we're going to invert multiply by it. So we have 18/5 times 5/6, x to the 6/5. And things can simplify there. 6 goes into itself once and 18 3 times, and the 5s cancel. Plus another constant c sub 2. So the thing is, when you're taking a constant for one antiderivative plus the constant for another antiderivative, and so on, adding constants, you still get back another constant, c. And so we don't have to write that constant c sub 1, c sub 2, c sub 3, dot, dot, dot. We can just put 1c in there for that. And so we get that our antiderivative is 2x cubed plus the 5th root of x to the 6 plus c. So you can always check your work by taking the derivative of your antiderivative. And if you do that, you should get back, so going back to your original equation or problem, you should get this piece in here. And this is called our integrand. Okay. So unfortunately, we can't just take something and manipulate it right away that we can take the antiderivative. Just same reasoning with derivatives. Sometimes we had to work with it to get it into a form. And so this is where U substitution comes in and is a great technique. It doesn't always work, but it is a technique that works and helps us to expand the different functions that we can take antiderivatives of. So I started going through U substitution with just an example. And your goal here is to find some piece of your integrand such that if you take the derivative of it, it's gonna cancel out with something else in your integrand, making it a simpler function. So I don't want you to see that piece yet. So we're looking at x squared over 2x cubed plus 1. So if you're looking at that, we can't manipulate that in order to take the antiderivative. If sometimes, I don't know if you did your homework, you saw that sometimes you only had one term in the denominator, and then you could rewrite it as a sum or difference of fractions and then move your power up so that it was in the power rule. You could use that power rule of antiderivatives. Notice that our denominator there, that 2x cubed plus 1, if you take the derivative of that piece, that gives you back an x squared. So right there, that should let you decide that you're going to choose u to be the whole denominator. So that's just one term. So I chose u to be 2x cubed plus 1. So if we rewrote this, I would still have x squared in my numerator. I would have my u down here in my denominator, because I just replaced what I chose u to be. And then I have a dx. So the problem here is now I have even a more complicated integral. I have now two variables in here, x squared and y squared, and I have a dx. My u is in terms of x. And so in order to deal with that, what you're going to do every time is you're going to take the derivative of both sides of your equation that you had chosen u to be. So if you take the derivative of a u, well, that's just 1. But we're going to tack on the du there because that was with respect to u. Think of when we were just doing implicit differentiation. We had to put in what we were taking the derivative of. So here, this 2x cubed, when we take the antiderivative of that, that gives us 3x squared. The derivative of a constant is 0. And we just took the derivative of the side with respect to x, dx. So if we can get dx by itself, we can substitute it back in here, and then it would be in terms of u. We had chosen things so things should cancel out nicely. So go back into the integral. And
can you scroll down a little bit?
Yes. So we are putting in dx, which is du over x squared. So once you've done that, notice your x squares are going to cancel. And now we just have an integral with respect to u, and we're integrating that with respect to du. So we get 1/6, 1 over u du. Remember the antiderivative, that's the special case where that exponent, if we brought that up into the numerator, is -1. And so the antiderivative of 1 over u is the natural log of u times that 1/6 out front, and then plus that constant c. But our original integral was with respect to, where's that going? Or with respect to u. So you have to go, with respect to x. So you have to go back in and replace what u is with respect to x. So we can always check this by taking the derivative of this antiderivative, and we should get back our original integrand, which was x squared all over 2x cubed plus 1. So I'm going to scroll past this one problem. I'm going to do one more problem of u substitution, then we can take a break. I guess I can quickly talk about it. Basically here, I could make it so I could take the antiderivative of this by multiplying out -4y plus 1 by itself 10 times, but that would be really tedious. And I probably would make some arithmetic errors when I was combining late terms or multiplying, distributing. So in order to get rid of that, we can also use u substitution here, because we can take the antiderivative of u to some power, and that's pretty easy. And if we choose what's inside the parentheses to be our u value, when you take the derivative of that, that's just a constant. So you're not going to have y left in there. So doing that, you're going to differentiate both sides of what you let u be. Well, derivative of u is always 1. So that's du equals, and the derivative of -4y plus 1 is just -4. Solve for dy. Divide both sides by -4. And now you're going to go back in and substitute what you had chosen. So plug in what you chose u to be. Plug in u what you had chosen that to be, and plug in the du. And so now you just have the integral of u to the 10th times du to the -1/4. If you pull the -1/4 out front, add 1 to your exponent, divide by your new exponent, and add c. Go back and do your substitution, plug in what u was, plug in -4y plus 1 wherever you see u in that expression. And we get the following: negative, parentheses, -4y plus 1 all raised to the 11th, all divided by 44 plus some constant c. Okay, so if we had the integral of 3x squared e raised to the 2x cubed dx. Okay, so remember the derivative of e to the x was one of the easiest functions to take the derivative of, right? Which was just e to the x. Well, if that's the case, then the antiderivative of e to the x is just e to the x. The problem is that exponent is not just a single variable, it's 2x cubed. So if we could choose our u value, since that's usually what you're going to look at if you have e there raised to some power, maybe see if that's what you want to choose, what you're going to take the derivative of. So notice if we chose u to be our exponent of e, which is 2x cubed, when we take the derivative of both sides, that's going to give me a square function. So that's going to end up canceling out with this 3x squared in front of my e. So looking at this, derivative of u is 1, so du, equals the derivative of 2x cubed. We'll bring our power down front, that's 6x, subtract 1 from our power, that's squared dx. We want to solve for dx. So divide both sides by 6x squared. We get dx is equal to the du all over 6x squared. So now we have the integral of 3x squared e raised to the u power, and then dx is du all over 6x squared. So notice things cancel. 3 goes into itself once, 3 goes into 6 twice. X squares are going to cancel. And so all we're left with now is 1/2, because I can pull out 1/2 outside the e to the u du. So take the antiderivative of e to the u. So we have 1/2 times the antiderivative of e to the u is just e to the u plus c. But we had chosen u to be 2x cubed. So this is 1/2 e to the 2x cubed plus c. So there's some tricks to this on what you choose. Like I said, you're looking at things that you can choose that are going to make your integration simpler. If you have e functions, sometimes using that power, see if you take the derivative, if that's going to cancel things out. That's usually a good trick. If you have fractions, sometimes and it's not one term in the denominator, maybe letting the denominator be your u value. If you have something raised to a huge power or parentheses, maybe choosing that inside. If you have a radical with an expression under it other than x, then maybe you're going to want to choose what's underneath the radical to be your u. But you're choosing your u value to be something that's simple or something that is going to make your integral simpler, and that is going to start to cancel out with something else so that you're only left with a antiderivative or integral of one variable. If for some reason you choose, and it's possible that this is trial and error and what you're going to choose your u value to be, it doesn't always come out nicely and you don't always choose it right the first time. So don't get frustrated on that. But again, choose things that are going to be, they're more difficult, but when you take the derivative, it's going to make it all simpler. And that when you go back in, everything is in terms of that variable. Okay, so let's take a break and then we'll come back and do some more problems. Okay, so we're gonna go back and look at some more examples. So let's look at the case maybe where we have y squared plus y in the numerator all over parentheses 2y cubed plus 3y squared plus 1 all raised to the 2/3 power dy. Okay, so right now we can't integrate that, so we need to manipulate it so we can. So if we have a denominator, usually maybe choosing that to be the denominator. But if we chose that to be the denominator, the whole denominator, then we'd have to use that chain rule. We'd have to bring down the power, we'd have to subtract 1 from the power of the inside, multiply by the derivative of the inside. So that's actually doesn't look like that would work. But what about inside the parentheses? So if we chose u to be this piece, when we take the derivative of it, our first term is going to be a squared, our second term is going to be a 1, so we might be able to manipulate it to get rid of that numerator. So differentiate both sides. Derivative of u is 1 du is equal to the derivative of 2y cubed is 6y squared, plus the derivative of 3y squared is 6y, plus the derivative of 1 is 0, and we just did that with respect to y. So let's divide both sides by 6y squared plus 6y, and so we get dy, which we were looking for, is equal to our du divided by the parentheses 6y squared plus 6y. So replacing, we have the integral of y squared plus y all over, we chose this to be u, but that u is still raised to the 2/3 power. And then our dy is really du all over. Well, before I write it, don't you notice that there's a 6 in common with these two? And then we want it to look like y squared plus y. So it would cancel with this. So let's just pull out a 6 from that term in the denominator there. So pulling out a 6, we get y squared plus y. And so now, simplifying, that y squared plus y cancels. We're left with the integral. I'm going to pull my constant out. So all I have in the denominator for the constant or coefficient is 6, and in the numerator, I'm left with a 1. So this is 1 over u to the 2/3 du. we want to rewrite this so that we can take the integral. And so we need to bring that u up into the numerator and rewrite it as the power. We can rewrite that as 1/6 times u to the negative 2/3 power. And so now we can use the rule to take the antiderivative. And so if we add 1, so u to the negative 2/3 plus 1, I'm going to add that 1 as 3/3, all divided by our new power, which is negative 2/3 plus 3/3. So negative 2/3 plus 3/3 is 1/3. And then I need to add on my c. So we have 1/6 times the reciprocal of 1/3, which is 3/1. I'm going to rewrite u. U was up here, was that 2y cubed plus 3y squared plus 1. So let's just put that in there. So 2y cubed plus 3y squared plus 1. In my parentheses. And this is a negative 2/3 plus a 3/3. So negative 2/3 plus a 3/3 is a positive 1/3 plus c. So we're almost there. 1/6 times 3, that reduces to 1/2. I'm going to rewrite the 1/3 power as a radical. So 1/2 times the cubed root of 2y cubed plus 3y squared plus 1, and then a plus c. Okay, so I want to go back and I want to look at a case where sometimes you have to manipulate it. You can't just use substitution and it would fall out, but it's with some more manipulation that will work. So let's look at the integral of 4r and then the square root of 8 minus r underneath the radical dr. Okay, so I suggested that if you had radicals, sometimes choosing what's underneath the radical is helpful. But notice the problem, if we choose the 8 minus r underneath the radical and we take the derivative of that, we're only getting back -1, and we're not getting an r left to cancel with the 4r outside of the radical. So we still have that, we'll have a problem that we have r in there and u. And so we need to do a little bit more manipulation for it to work. I can't distribute this 4r inside of the radical, but if we could get this as one term here, we could rewrite that as u to some power, and if we could rewrite 4r in terms of u, then we could use rules of exponents to rewrite it. So that's kind of our goal, but let me show you how it works. So when we're choosing u, again, we want to choose, in this case, what is underneath the radical to make things simpler for us. And so we're going to let u equal 8 minus r. So the derivative of u is du is equal to the derivative of 8 minus r, which is -1 dr. So dr is equal to -du. So rewriting this, we get 4r square root of u times -du. Okay, so again, nothing unfortunately cancels. To get rid of that r, we need to manipulate this so it's just in terms of u. And so how we're going to do that is we're going to go over here and let's solve for r. In terms of u. Okay, so I want to get r by itself. So if I subtract 8 on both sides, I get u minus 8 equals negative r. If I multiply both sides by negative 1, I would get r is equal to, I'm just going to change the signs here and write the 8 first. So this would be 8 minus u. So if we go back up here now, we can replace what r is in terms of u. So doing that, we now have the integral of 4 times r, but r was 8 minus u, all times the square root of u. Okay, so let's rewrite that square root of u as u to the 1/2 power times negative du. So I don't like that negative with the du, so let's pull that negative out front in front of the 4 maybe. So negative 4, and then this is du. So we technically can pull that negative 4 out in front of the integral if we want. It's still not quite in the form that I can integrate. It is in terms of u, but I notice that if we distribute that u to the 1/2 or negative 4 times u to the 1/2, then we can integrate it. So let's pull the negative 4 out in front of the integral, and then let's distribute u to the 1/2 to each term inside the parentheses. And so doing that, we get 8 times u to the 1/2 minus u to the first times u to the 1/2. Rules of exponents, you add, same base, so 1 plus 1/2. So 2/2 plus 1/2 is 3/2. I technically need parentheses around that whole integrand and then the du. Okay, so now I can just take the antiderivative of each piece. Be careful because that negative 4 is out there and so it has to be distributed. And so now if we take the antiderivative of 8u to the 1/2, so it's 8u 1/2, we're going to add 1 to it when we take the antiderivative, all divided by 3/2. So I don't know if you've noticed, but when we're dividing by a fraction, we're multiplying by the reciprocal. So if I'm dividing by 3/2, I multiply by 2/3. Minus u to the, so I'm going to add 1 to my exponent of 3/2. So adding 1 would make it 2/2. So dividing by a fraction, I'm just going to rewrite it as and multiplying by the reciprocal. So 3/2 plus 2/2 is 5/2. So flip it up, this will be 2/5. And then we have some constant plus c. Actually, let's close off the parentheses. We could distribute the negative 4 to the constant c, but then we still have a constant c, so it doesn't matter. I just pull it out there. So we have negative 4 all times. So nothing simplifies here with the numerator denominator. We know we multiplying fractions, you multiply the numerator, so 8 times 2, so that gives me 16 all over 1 times 3. So this is 16/3 u to the 3/2. So u to the 3/2, let's just write it. Minus, so nothing cancels here, let's put the 2/5 in front. U to the 5/2 plus c. Okay, so we need to go and replace what u is. u is equal to the 8 minus r. I can distribute that -4, I don't have to. And then I could rewrite these as radicals if I want. So 16/3, replacing u, we have 8 minus r. This 3/2 power is the same thing as the denominator is 2, so it's a square root of 8 minus r cubed. Minus 2/5. And then I see a u there, so square root 8 minus r. And this is to the 5th power. And then plus c, in parentheses plus c. Okay, so there's a case where we needed to do a little more manipulation, where we had to, when we chose u, it didn't cancel out. There was no way that you could choose u for it to cancel out. But making it as one term underneath that radical, it made it possible that we could distribute and use rules of exponents, where our original integrand, we could not do that. Okay, so we haven't talked about how to take the derivative of logs. And so if you see a log in your antiderivative, then that might be what you want to choose u to be. So let's look at a case where we have logs or natural logs in that equation. Bigger. Okay. Okay, so we have 1 plus, so the integral of 1 plus 3 times natural log of x. That is all raised to the 2nd power. And then this is divided by x dx. Okay, so like I said, we don't know how to take the antiderivative of natural log of x. So that might be what you want it to be. But we have a parentheses there, and taking the derivative of that constant is just going to go away. And so let's just choose our u value to equal to what's in that parentheses in the numerator. So 1 plus 3 ln of x. So take the derivative of both sides, we get du is equal to the derivative of 1, which is 0, plus the derivative of 3 times natural log of x, which is just 1 over x. And then we have that dx. So we want to get dx by itself. So basically, this is 3 over x dx. If we multiply by the reciprocal, so x over 3, we would get x over 3 times du. Okay, so let's go back in and replace what u is and what dx is. So we have the integral here of u squared all over x times du, and du is x over 3 du. So notice our x's cancel, which we needed to happen, or we would have had to do some more work. And now we have the integral of u squared. We can pull that 1/3 out front of u squared du. So add 1 to our exponent when we take the antiderivative. So that gives me a cubed all over my new exponent of a 3 plus c. This is 1/9 times u. So we're going to go back and replace what u was, which is this 1 plus 3 natural log of x. And that is a square. No, that's a cube. Plus c. It's not too, I guess I say that a lot. Not too bad, guys. Kind of fun. It's just a puzzle. Just manipulate it. It will all come out pretty clean. Any questions? Okay, so let me see. There might be some distractions in the background. Let me look and see if I see any other ones that might look good. Okay, so here's where you might want to go backwards with application. So I was saying that the antiderivative is helpful because that undoes the derivative. And so I don't know if you guys realize, but when you take the marginal cost or marginal revenue or marginal profit, that's basically the derivative of that function. And so if you're given one of the equations for marginal profit, cost, or revenue, we can find the original function by taking the antiderivative of that marginal function. And so let's say that you're given the marginal revenue in thousands of dollars for the sale of an MP3 player. Sale of X MP3 players is given by the following. And so they give you that R prime of X. This is equal to 4X all times X squared plus 27,000 all raised to the negative 2/3 power. So part A, and X is equal to, let's just put that there. So the revenue in thousands of dollars from the sales of X and MP3. Number in thousands of MP3 players. So find the total revenue function if the revenue from 125 players is $29,591. So find R of X if the revenue from 125 players is $29,591. Okay, so that bit of information is going to help us to figure out what that C value is when we take the antiderivative. And so we want to first take the antiderivative of this. So we can find out what R of X is. R of X is equal to the antiderivative of R prime of X dx. So R of X in here is equal to the antiderivative of 4X X squared plus 27,000 raised to the negative 2/3 power dx. So we need to choose what u is going to be. I noticed that we have that x outside of the parentheses that's raised to a negative 2/3 power. So choose u to be what's inside the parentheses in this case. So let u equal this x squared plus 27,000. So du is equal to, derivative of that is 2x dx. Solve for dx, we can divide by 2x, we get du over 2x. We're going to go back and substitute in. And so this is equal to 4x, or the integral of 4x all times u raised to the negative 2/3 power times, and dx we're replacing with du over 2x. So things cancel nicely. 2x goes into 4x twice. We can pull that coefficient out front and take the antiderivative. So the antiderivative of u to the negative 2/3 power. So add 1 to our exponent. So negative 2/3 plus 3/3 is 1/3 times the reciprocal, because we're dividing by that, of that new power. So this would be 1/3 plus c. So this gives us 2/3 cubed root of whatever u was, and u was this x squared plus 27,000 plus c. And so now we want to figure out what c is. Okay, so this is where I'm not sure in the problem if they, when they told us that was 125 players, if they were considering that as 125,000 players, because they said X was in terms of thousands. Maybe I should reread that. So the marginal revenue is in thousands of dollars from the sale of X MP3 players. So I kind of think I wrote that down wrong. X is equal to the number of MP3 players. And R of X is in thousands of dollars. Okay, and so this piece right here, they actually give me what my X value is, 125 players. This right here, this is 29,591 players. And if we wrote this in terms of thousands, this is 29.591 thousands of dollars. So let's go back in there. We want to plug in those values so that we could figure out what C is. So if I go back in here, I have 29.591 is equal to 2/3 cubed root. My X value, that was 125, so 125 squared. Plus 27,000 plus C. So I'm going to square 125,000 and then I'm going to sum that to be to 27,000. And so that gives me 42,625. But I need to take the cubed root of that number. Oops. I don't know how to do that. So let me just clear that one more time. So that raised to the 1/3. This is what I got, and I'm approximating now. So 29.591 is equal to 2/3 all times the cubed root of 42,625. I got 34.93. 2 plus C. So let's divide that number by 3 and multiply it by that 2 in front. So I have 29.591 is equal to, so times 2, divided by 3. That gives me about 23.288 plus C. So subtract that, 23.288 from 29.591. We get that C is equal to 6.303 approximately. Okay, so we now have our revenue function that we can find how much our revenue is going to be selling X number of MP3 players. And so R of X is equal to 2/3 cubed root of this X squared plus 27,000 plus what we just found C to be, which is 6.303. So there was an example. I know I don't usually have time to bring in some of the applications. So there's an application using U substitution. So we were just looking at antiderivatives as undoing the derivative. So but derivative or antiderivatives integrals also represent areas under the curve. And I believe that's what we're going to look at next, last part of this course. So that's all for today with that material. Okay, so I did make an error in here. At this step, I was talking to you about multiplying by the reciprocal of our new denominator, but I didn't do it. I multiplied by our new denominator. So reciprocal here would have been 3. Oops. And so that would have changed things in here. This would have been a 6. This would have been a 6. This would have been a 6. Yep, and it was a minus negative 180. So 6, let me do that real quick. So 6 times our 34.932. That's 209.592. Oops. So I already did that. So let's subtract that on both sides. And it's telling me they're getting negative. Oh, that is right. They're getting C is negative 280, or is negative 180. So C is equal to negative 180. So minus 180 here. And I got to change this piece right here. This should have been a 6. Okay. So I'm glad one of you were here and that saw that error. It might have taken me a while before I had found where I got that. So thank you.